Good afternoon, everybody. Myself Akshay Jilova, and I am here to discuss the topic Color TV Part 1 under the subject Consumer Electronics. So, under this topic we will be covering the following. Number 1, the introduction of color TV, what the color TV all about is, how does it work, compatibility of color with monochrome, color television systems, various systems, 3 color theory, how the colors are formed, characteristics of color, and color TV camera tubes. So, these will be the some of the topics which will be covered under this. Number 1, the introduction part, color TV systems and following information. Number 1, color and brightness information of scene, sound associated with the scene. As we know, television is all about the picture information, but with that picture we send the sound signal also. So, these are the two variables. Then compatibility. Compatibility means the color television signal must produce a normal black and white picture on a monochrome receiver without any modification of receiver circuitry. Number 2, the color receiver must be able to produce a black and white picture from a normal monochrome signal. This is referred to as reverse compatibility. So, these are the two constituents of compatibility. The first two, one, the color TV signal must produce a normal black and white. If it is a color TV and the input signal is black and white, then the television and the system overall system should be able to produce that in black and white corresponding information. Second, the color receiver must be able to produce a black and white picture from a normal monochrome signal. If it is a monochrome signal at the input and the system is color, then it should also be able to display the same in the same proportion. So, this can also be called the reverse compatibility. And how the compatibility can be achieved? To achieve this, and this is to make the system fully compatible, composite color signal must meet the following requirement. There are some of the requirements which are to be satisfied when if the system has to be compatible one. Number 1, it should occupy the same bandwidth as the corresponding monochrome signal. So, it means the bandwidth of monochrome TV and color TV system should be same, and it is same. Second, the location and spacing of picture and sound carrier frequencies should remain the same. So, when we talk about the bandwidth of the system, then the location and spacing of the various parameters of sound and color and other carrier frequencies, that should remain same. That it means it should be located at the same place where it is located when it is monochrome, or if it is color. The only difference between monochrome and color is that color picture or color information is multiplexed with the monochrome signal. So, the location of other signals should remain same. The color signal should have same luminance, that is brightness information as would a monochrome signal have, transmitting the same scene. The luminance is equivalent of brightness in monochrome, whereas in monochrome we call it brightness, in color we call it luminance. So, it should be same whether it is color or it is black and white, it should remain same, or it should be the same when means compatibility means if it is color TV, the luminance should be equal to the brightness if it is monochrome TV, when the scene being transmitted is same. The composite color signal should contain color information together with ancillary signal needed to allow this to be decoded. So, the composite color signal should contain the color information together with the ancillary signal needed to allow this to be decoded, means the signal should be provided at the same location, and it should be, as I said earlier, it is multiplexed actually. So, when it is decoded, it is whether it is black and white or color information, it is decoded in the same form. The color information should be carried in such a way that it does not affect the picture reproduced on the screen of a monochrome receiver. So, as we are aware that color picture is nothing but it is monochrome picture, and then colors are added to that monochrome picture, as if we trace a picture and then add color to that picture. Similarly, in color TV, it is the monochrome picture and colors are added to that monochrome picture. This is the additional signal, color signal, which is provided. So, it should be carried in such a way that it does not affect the picture reproduced. So, when it is supplied like this, when it is multiplexed, it will not interfere with the actual monochrome picture, and it will be available on monochrome screen, monochrome receiver screen. If it is the monochrome receiver screen and input is the color signal, then minus color other information will be displayed. It means it will be the corresponding black and white information in the same proportion that will be displayed. The system must employ the same deflection frequencies and sync signal as used for monochrome transmission and reception. System should be identical, all the signals, that is deflection frequency and sync signal, they should be at the same location, and the same frequencies are to be retained, whether it is color system or it is monochrome system. Only then the system will be compatible. And in order to meet the above requirements, it becomes necessary to encode the color information of scene in such a way that it can be transmitted within the same channel bandwidth of 7 megahertz and without disturbing the brightness signal. So, for color signal also, the channel bandwidth is same, that is 7 megahertz, as it is for the monochrome signal. All the signals, all the sync signal, picture information, sound signal, guard band and color information, all that is carried within that 7 megahertz. If it is the monochrome system, even then we have 7 megahertz, and if it is color system, then also we have the same 7 megahertz bandwidth. Similarly, at the receiving end, a decoder must be used to recover the color signal back in its original form for feeding it to tricolor picture tube. So, actually what happens at the sending end, what we do, we collect the color information, and when we collect the color information, that information, the color signal is multiplexed with the original monochrome signal, and then it is transmitted. And when it is transmitted, as it has been pointed out earlier also, during the transmission in the bandwidth is same 7 megahertz, and the location of all the frequencies, that is sync signal and your other color information and sound signal and other signals, all the signals are located at the same position. And when signal is received at the receiving end, then what happens, it is decoded, and when it is decoded, then color information is get from that decoded signal, and when that color information is received, that color information is supplied to the tricolor picture tube. Picture tube of color TV and monochrome TV are different. For color TV, it is tricolor picture tube. So, that color signal is supplied to those 3 electron guns. This figure will show the compatibility. Brief here, we can see that this is monochrome camera and this is color camera. Here we have one electron gun, and here we have the 3 guns, and we before those 3 guns we have optical filters. These filters are meant for filtering the incoming signal, and they are being divided in 3 different primary colors. This through this filter only the frequency or wavelength corresponding to the red color is allowed to pass through. From here only green color frequencies or bandwidth will pass through, and here the frequency which lie in the bandwidth for the blue, that will pass through. And this RGB, red, green and blue, these 3 primary colors are thus obtained, or the actual scene is divided in 3 different parts, 3 different frequencies actual, and this is for red, this is for green and this is for blue. And with the help of a combining network, this is combined here and then it is transmitted. This is the transmission path, and in the transmission path it is the same frequency, it is the same position, and it is the same bandwidth which is required for both the systems and which is being used for both the system. And this shows, these arrows, these show the compatibility, that if it is the color picture, it can be displayed in color receiver and it can be displayed in monochrome receiver also. If it is monochrome, it can be displayed in monochrome and it can be displayed in color receiver also, right. So, this is how the system becomes compatible. The same system, when it is able to display the signal on both the rasters or both the receivers, then it is called the compatible system. Here again we have those 3 RGB and 3 electron guns. As these signals were separate here, similarly after receiving here, after decoding the signal, whether it has been received from the color or it has been received from the monochrome camera, it is divided in RG and B. If it is and then this is the corresponding luminance and brightness level which is displayed here. Red, green and blue phosphors are there. We will discuss that in detail in the chapters to come or topics to come. And red, green and blue, these 3 signals are treated differently. There are 3 electron guns and these 3 electron guns are responsible for the transmission of electron beam from the electron gun to the final phosphorus coating, where the signal is being displayed in the form of light. So, if it is black and white information, that will be displayed in black and white or monochrome. If it is color, that will be displayed in corresponding color information. Similarly, here it is monochrome receiver, and in, as we all know, in monochrome it is the single electron gun from where electrons are being emitted and they strike with the phosphorus coating and a light is produced. So, this is the signal transmission path illustrating compatibility between color and monochrome TV systems. RG and B represent 3 camera tubes which develop video signals corresponding to the red, green and blue contents of the scene being televised. So, the scene which is being televised, its red, green and blue equivalents or corresponding colors are being generated there. If it is the color system, and if it is monochrome system, then in that monochrome system the corresponding brightness level of red, green and blue is displayed. Now, we will discuss what the natural light is and how the colors can be formed from the natural light. When white light from the sun is examined, it is found that the radiation does not consist of a single wavelength, but it comprises of a band of frequencies. It is not a single wavelength, but it is a band of frequency. There are various frequencies and it is a band, it is a range or a set of that frequency. In fact, white light is very small part of the large spectrum of electromagnetic waves, which in total extend from very low to beyond 10⁻25 hertz. The visible spectrum extends over only an octave that centers around a frequency of the order of 5 into 10⁻14 hertz. The visible spectrum has been expanded and shown separately to demonstrate the range of color it contains. Note that the various colors merge into one another with no precise boundaries. This we will see from here. This is the region of sunlight in the electromagnetic spectrum. This is a spectrum of electromagnetic radiation, and this is visible spectrum. The spectrum which we can see, it is only a very small part. It is a fraction of the total spectrum. This is spectrum of electromagnetic radiation. It starts from very low frequency and it goes up to 10 raised to power 25 and more. So, this is the visible spectrum, and it is extended from 780 nanometer to 380. So, this is the band over which this visible spectrum is being expanded, and within this visible spectrum, this is the sunlight, actually this is the sunlight. So, within this visible spectrum we have different colors, as it is red, orange, yellow, green, blue, indigo and violet, right. So, as we all are familiar with, it is called VIBGYOR: violet, indigo, blue, green, yellow, orange and red. So, these are the different wavelengths at which will presume a color to be different from other, because it is of a different wavelength. The signal is of a different wavelength, the frequency is of a different wavelength. If it is 400, you will see it as violet. If it is 500, we will see it blue. If it is 600, we will see it as orange, and if it is 700, we will see it as red. So, as it is clear from here, there is no specific frequency or the wavelength for which you can say that this is for a particular color and next is for the next color. These colors are considered to be merged into each other. Just yellow fades out and orange starts, and from here, from the orange it gets converted into red, and similarly from yellow it is converted into green, and then blue, indigo and violet, and in between it is the intermediate color. It is neither indigo nor violet, it is a color somewhat in between there. Similarly, from yellow and orange, when it switches over from yellow to orange, it does not switches itself abruptly, but it merges into the next color. So, this merger is seen as the continuous form of the colors, because this is the radiation. So, this is natural light, how the colors are seen from that light. This is the visible spectrum, whereas this is the whole electromagnetic radiation spectrum. So, we are concerned with this visible spectrum only, whether it is white, dark, black or any color. So, that lies within this range. Apart from this, we are not able to see the colors. Color TV system, what the color television systems are, and what are the various types of color TV systems. There are three color TV system in the world. The first is the American NTSC, National Television System Committee. The other is the German system, phase alteration by line, PAL, and another is French system, which is called SECAM. So, these are the three color systems which are famous worldwide: the American, the German or European we call it, and the French system. So, these are the three systems, and we are mostly concerned with the PAL system, because we deal with this system. Color perception, how the colors are perceived, how we see that this is a particular color. Nature of light, visible spectrum, white light. It is when entire visible spectrum reach eyes in suitable proportion, then it is called white. So, these white is not actually white, it is the various proportion of those three primary colors which we say. If it is mixed in the right proportion, then that will lead to a white light. VIBGYOR, we just have discussed VIBGYOR: violet, indigo, blue, green, yellow, orange and red. These are the various 7 colors which we see in the visible spectrum. Range of wavelength. So, range of wavelength of this the visible spectrum, it is extended from 380 to 780 nanometer. This is the wavelength over which the visible spectrum is available. Color perception, these are following are some of the prerequisites of for that. Human eye, so how to see the color, you require human eye. Lens assembly, it is within that. Retina at the back of the eye, light sensitive organs, and next is according to theory of formulated by Helmholtz, the light sensitive organ are of two types: rods that sense brightness of object and cones that are sensitive to color. So, the human eye, uh, how it sees the colors, with if you see some object or some scene, from that scene there are rods which are responsible for the sense of brightness of the how much bright a particular object is, that is sensed by the rods of the eye, and cones are sensitive to colors. What is the particular color of that object, that is sensed by the cones. So, these cones are formed at the retina of the eye. Color perception, three set or group of cones, as I just told you, those three primary colors, red, green and blue. One set of cone detect the presence of red color in object focused on retina. The second set of cone perceive blue color, and the third is sensitive to green. So, these are the three basic colors. Three color theory, how the colors are formed, it is based on these two theories. One is additive color mixing and second is subtractive color mixing. Now, we will discuss what the additive color mixing and what the subtractive color mixing is. In additive color mixing, basis of any color television system is the additive color mixing. Light from two or more colors obtained from independent source or through filter can create a combined sensation of different color. The example has been taken. If it is red and green, then it will be perceived as yellow. If it is red and blue, we will see it as magenta. So, this is how colors are formed. There are these three primary colors, red, green and blue, and it depends upon the proportion in which those three colors are being mixed, that what the resultant color is. We have taken the two examples here. Suppose we have only two colors, that is red and green, and if they are mixed in that proportion, then they will give you the yellow color. Similarly, if it is red and blue, if they are mixed, then we will see the resultant color as magenta color. This is more clear in this picture. It is red, yellow and green. These are the three colors: red, blue, green. If green and red is mixed, it becomes yellow. If red and blue is mixed, it becomes magenta, and if blue and green is mixed, it becomes cyan. So, these are the examples of additive mixing, that if we mix three colors, the resultant color will be different. It depends upon the proportion in which it is being mixed, and if these three here we can see in this area, here it is red also, it is green also and it is blue also. If it is mixed in right proportion, then we will see it will give us the resultant color, which is white color. So, the white color which we see, it is the combination of these three colors, red, green and blue. If these three colors are mixed in right proportion, then we will have the resultant color as one color, which is called white. So, this is called additive mixing, means when two colors are added or more than two colors are added. Here it is two color, here it is also two color, here it is also two color, but here it is all the three colors, green, red and blue. So, if two or three primary colors are mixed with each other, then resultant color formed is a different color, and that is called the additive color mixing. This diagram shows the effect of projecting green, red and blue beams on a white screen in such a way that they overlap with each other. So, here the red and green are overlapping, here red and blue are overlapping, and here blue and green are overlapping, and in this area all the three are overlapping. Next is subtractive mixing. Mixing is done by using the reflecting property of pigment, and it is used in painting and color print. In color print and painting, what we do, we have the original white, and in that white we add some other color. It is actually not addition, it is the subtraction, and you all might have seen that this subtractive color is subtractive mixing is done when we use the painting and other coloring. Grassmann's law. According to this law, eye is not able to distinguish each of the color that mix to form a new color, but instead perceive only the resultant color. Eye behave as output of three cones are additive. So, it is always additive mixing which is being observed by the eye, because eye is not able to distinguish each color. We cannot distinguish each color, but what we see, it is the resultant of those three colors, and the resultant is neither but it is mixing. So, what we see, it is the mixed color, what we perceive is the resultant color. The brightness impression created by the combined light source is numerically equal to the sum of brightness of three primary colors that constitute the single light. So, what apart from the color, the resultant color, it is brightness also which is important. So, what will be brightness of the resultant color? It depends upon the brightness of individual primary color. When two or three primary colors are mixed, then according to Grassmann's law, the brightness of the resultant color will be nothing but it will be the resultant or numerical addition of the brightness of individual primary color. Means if red, green and blue three are mixed and white color is formed or some other color is formed, then what will be the brightness of that color? That will depend upon the individual brightness of the primary color. What was the brightness of red, what was the brightness of green, and what was the brightness of blue color. So, numerically if we add the brightness level of all these three colors, that will give the brightness of the resultant color. Next is color characteristics. What are the characteristics of color? Any color has three characteristics to specify its visual information. These three characteristics are luminance, hue and saturation. So, now we will discuss these three, luminance, hue and saturation, one by one. Luminance, what the luminance is? Amount of light intensity as perceived by eye regardless of color of object. So, as I explained earlier also, luminance is nothing but it is equivalent to brightness in black and white or monochrome TV. So, what the luminance is? It is the intensity of light perceived by the eye, irrespective of the color of the object. Whatever the color of the object may be, irrespective of that, what is the brightness level of, what is the light intensity in that color is, that is called luminance. Different color has different brightness response to eye. We all know as different color have different brightness level. Some colors are very fast, very shining, some colors are dull. So, that is the brightness level of that particular color. Dark red appear black, yellow appear white and blue appear gray. So, this is the actual equivalence of brightness and luminance. If we have, as we just have discussed the compatibility, if we have a compatible system and if you see the color information being televised from somewhere and that is being received by the monochrome receiver, and in that monochrome receiver what we will see? We will see if it is red color there, then that will appear black in the monochrome system. If it was yellow, that will appear white, and if it is blue, that will appear as gray. So, this is the brightness equivalence. So, that is Luminance is the brightness equivalence of monochrome. Next is hue. It is predominated spectral color of the received light. How dominant a particular color is, predominance of any color. Color of object is distinguished by its hue. Different hues result from different wavelength of spectral radiation. What the hue of a particular color is